Great. So thank you very much to the organizers for putting on this very nice meeting. It's really it's been great to come here and learn lots of new things. So this is going to be a bit different, I think, from most of what we've heard. But it's really all about this macroscopic fluctuation theory idea. And it's really about sort of model building and thinking about using MFT maybe in slightly different contexts than what people usually do. So it's going to be rather qualitative, but maybe that's okay before lunch. There'll be pictures. I'm happy to take questions as we go. There is kind of some mathematics behind, but I won't show so much because I think for you guys it's probably not so important, the detail. Okay, so this is work with Tal Agranov, who is a postdoc in Cambridge with me and with Mike Cates, and Etienne Fodor, so this is one set of collaborators. And then also with James Mason, who was a student in Cambridge with also Maria Bruna. And we did some work with Clément Erignoux, who is really a probabilist. So Maria is kind of applied mathematics, Clément's probability, Mike and Tal and Etienne and me are really all physicists. So there's a kind of combination of different things going on. So I'll give you some motivation for what this active matter business and why people care about it and why you might be interested. And then I'll talk about lattice models for active matter. And I'll try and do that in a sort of general way to give you a sense of what is our sort of philosophy in doing this kind of work. And then I've got a bunch of examples for illustrative results, which I can go through more quickly or more slowly, depending on whether anyone's interested enough to ask questions about specific ones. So as I said, I'm happy to take questions as we go, and then some. Okay, so what is active matter? So active matter is kind of being studied a lot in statistical physics at the moment, and the way people usually talk about it is you have systems of interacting particles, but each particle is somehow taking up some fuel from its environment, and it's using it to do some work. For example, to propel itself forward, or to pull and push on other particles, or to do something like this. So the examples people usually talk about are animals, so like flocks of birds or shoals of fish. So you think of each bird as a particle. It has some self-propulsive force taking it forward. It interacts with its neighbors in interesting ways, and some collective phenomena emerges. Or you can think of it on a different scale. You can think of swimming bacteria, or robots, or there are synthetic colloids which behave like this if you supply some chemical fuel to the medium. Or you can think about biological filaments and motor proteins, something like this. So motor proteins, they kind of take some ATP and they use it to do work on other filaments, usually. So, oh, never mind. So I'm not going to talk anything about biology or birds or animals or anything. So I'm interested in this, really, at least for today. We consider many body interacting systems with self-propulsion, so they're non-equilibrium systems, and we're doing them as prototypical models for non-equilibrium statistical physics. So we're hoping to find some interesting new physics in models that are inspired by this kind of collective behavior. Okay, so what's this sort of benchmark example? So I'm going to go on to the lattice later, but let's just start in the continuum. So let's suppose that we have some particles, and at time t, particle I has position xi, and it's going to be in 2 dimensions for convenience. We could do 1D, we could do 3D, but we'll do 2. And we're going to have n particles. And then we write some sort of SDE for the position of particle I. So you feel some gradient force from interactions with other particles, and maybe from some container in which you live. So this is some sort of equilibrium-like interaction with the other particles and with the walls of the container. And then this is some sort of Brownian noise, so this would just be an equilibrium model. And then what's added to the sort of traditional model is the self-propulsion force. So this is a force. Okay, maybe there should be a mobility, but you can think about it as a force in the equation of motion. And it's describing the self-propulsion of particle I. And for convenience, we can just think about it as a unit vector, but it has some direction, which is doing some interesting things. And then there's a few choices for what you could put here. And there are many choices, but there are 2 main classes of model, I would say, at least for the purposes of today. You can either take each of these unit vectors to be an independent random variable, which evolves in time, has mean 0, and some correlation time tau. So think of it as a unit vector that's evolving at random on a circle, maybe. That's a good example. That's called an active Brownian path. Or alternatively, you could say that these UIs, they don't evolve independently, but they like to align with those of other particles nearby. So this would be like a colored noise, like a colloidal particle with a colored noise, and this would be like a bird which tries to fly in the same direction as the neighbors of the other birds that are around. Okay, so those are the 2 main classes, I would say. And then there's 2 main kind of phenomena. I mean, there are many phenomena that can happen, but here are 2 of the interesting ones. So if you have the first type, if you have unit vectors which evolve independently of each other, but with a correlation time tau, which is fairly long, that tends to lead to phase separation. Oh, sorry, sorry. So I said unit vector, so you should imagine, sorry, a vector of fixed length. It should be a coefficient in front if you want it to be unit vector. Okay, sorry. So So here's the sort of classical picture of motility-induced phase separation. So these are particles. It's a computer simulation of, like, I don't know how many, probably 10,000 or 100,000 particles. They evolve in 2 dimensions. They repel each other. They don't have there are no attractive forces between these particles at all. There is only a persistent colored noise. And what happens is phase separation. And this was became exciting maybe 15 years ago. And there's been a lot of work trying to understand, essentially, is this like liquid vapor phase separation or not? I would say that's the key question in this business. And the answer is sometimes it is and sometimes it isn't. It has some things that are the same and some things that are different. And then the other kind of class of models, if you have alignment, then you have this kind of Vishek type models, which go back even longer, maybe 30 years. So what you're seeing here is each particle is represented by an arrow, and the arrow indicates the direction in which the bird is flying, for example. And there are no attractive or repulsive interactions here. The flocking is induced by the fact that they tend to align with their neighbors. So when you're near some other birds, you tend to fly the same direction. That means you tend to move together for a while, and you get this kind of flocking there. And both of these things have been studied a lot in physics, but now we want to do kind of MFT modeling of these kinds of things. So we want to put these models on a lattice, and hopefully that gives us some extra new insight. And in particular, what it might do for us is, this is quite an expensive computer simulation, but if you had an accurate hydrodynamic description, you wouldn't have to simulate 100,000 particles. You could just simulate a density and maybe an orientation on a grid, and that would probably be easier. And maybe you could have sharper conclusions about phase transitions and other interesting things that I have. There is repulsion in this case, and not in this case. So there's a tube body equilibrium-like repulsive. Oh, hey, did you have one? Or?
Like the size is fine.
The size of what is fine? Sorry, there. It's liquid vapor, so think of lever rule. Think of lever rule. So there's a density it likes to have. So yeah, it's classic phase separation. Yes, yes, exactly, yes, that's right. Yeah. If you did like a constant pressure ensemble, or yes, I think yes. Well, one way or the other, it would go to all liquid or all vapor, presumably. Great. Okay. Right. So let's try and put this stuff on a lattice. And this story starts with this paper of Murtaza Kubran-Hussein, Clément Erigneau, Thierry Bourdieu, and Julien Trailleur. I think this is now the right date. I showed this slide before with the wrong date, but I think that's now the right date. Okay, so what they did, they considered a one-dimensional lattice model, simple exclusion, so at most one particle per side, but 2 species of particles, which here are kind of purple and blue, and the 2 particles represent the orientation. So the light blue particle is a left mover, the purple particle is a right mover. And the picture is supposed to tell you everything, but just to be sure, so particles hop to nearest neighbors with rate d, and what's special about this model is that they can swap places. So it's not like classical SEP. Particles can swap places with rate d, plus and minus. So that's not the kind of classic SEP, but never mind. And then the minus particles are a bit more likely to move left than right, and the plus particles are a bit more likely to move right than left, and that's what this self-repulsion force is doing. But you see there's a 1 over L here, so L is the number of lattice sites. Okay, so that's like, and it's like the WASEP scaling, so there's 1 over L here, that makes it like WASEP. And then particles change direction with rate gamma over L squared. So even slower than the WASEP, they can change color. So the right movers become left movers, and the left movers become right movers, but this happens very slowly. This happens on the order 1 scale. Okay, and the self-repulsion does not affect the swapping. So that's the choice they made. It might not be the most natural choice, but that's the choice they made. That when you're deciding whether to swap places, if you're a left mover and you're deciding whether to swap places with a right mover, you don't care about orientation. Okay, and then this model supports motility-induced phase separation. If you just put it on the computer, you see something like this. So you see a dense liquid, dilute vapor. Okay, this is in 2D, this is in 1D. It's easy to see how to generalize this to 2D, I hope. And then inside here, there's a bulk with a well-defined density. Out here, there's a vapor with a well-defined density. And then there is some interfacial region. And the interfacial region on the left is dominated by the right movers. Okay, just to be clear, species alpha can be plus or minus. It hops from I to a vacant site, this, with a rate, which depends on its orientation and the direction of the hop in this way. So right movers like to go right, left movers like to go left. Okay, and then the adjacent particles swap places with rate d, independent of anything. And then they change direction with this slow rate gamma. Okay. So this model is a bit funky, as always with WASEP. because the particle transition rates depend on the system size. And you might not like that, but that's what you have to live with if you want to have exact hydro for this kind of model, at least at the level of maths that I understand. And that means that the critical properties of the system are going to be mean field, it turns out. So if you're interested in critical exponents, then sorry, there's not going to be any interesting critical exponents in the following because they're all going to be mean field. So if you want to do something else, then you'd have to do a different kind of rescaling, basically. Okay. So then what you do, okay, what the mathematicians do is they re-embed the lattice in the unit interval, and then you speed up time by L squared, and then you get some equations of motion, which are the hydrodynamic equations of motion. So you take hydrodynamic limit, you get deterministic equations because law of large numbers, so on and so on and so forth. And they look like this. So you have diffusion, you have advection in more or less the way that you'd expect. You have this extra factor of 1 minus rho that you might or might not expect, depending on what you thought about it. And then here is the species flip, which just turns out to be linear. And the reason for these funny factors of L is to make sure that all these things appear in the same order in this equation. And this can be generalized to 2-dimension, that's easy. And it can be generalized also to the case where you swap places between the particles, where you don't swap places between the particles. So this place swapping move is a bit unnatural from the point of view of set, maybe. You can turn it off, but then it's much harder to derive these equations, and they are a bit different looking. I'll tell you what they look like a bit later. But this is, okay, never mind. So Clément's thesis with Thierry Bourdieu was really mostly about this case, and then they did this swapping case later. Okay, so is that clear? That's the kind of model that we're interested in, and the kind of phenomena that it produces is this motility-induced phase separation, for example. So interesting phase transitions. Yeah. The 1 over L's? I mean, okay, so I guess so maybe Kieran would have something to say, but one thing you can say is that if you do this, and then you make the coupling kind of fairly big again, then you start to recover the physics that you kind of want from the finite L. So WASEB is not sick in the sense that it gives you usually the right qualitative behavior. It gives you the wrong critical exponents in this example. But it's really for tractability, I think. But because this, don't ask me about it, but this is really rigorous. So there's really a theorem for this, and also for this case as well. So in the book of Kipnis-Landim, it's 400 pages. But yes.
If you don't do that, it will be more physical, but this would be an expansion in like a derivative order. Diffusive part will be of lower order, and
exactly.
You have to deal with.
If you put epsilon in front of t, then I mean, okay, these people, they care about existence and uniqueness of these things, and at least you have existence if you don't have any epsilon here, and you can prove convergence to local equilibrium and everything that you want.
Yeah.
Which is all much harder. I mean,
As you. But somehow it's not exactly the physical case that you would like to
I agree.
write out.
I agree.
The nicer case mathematically.
I agree. So we do this simplified thing, we try and learn something, we understand that we are not simulating the most natural thing because the particle properties depend on the systems. Great. So, oh no, you want to say something? Or?
No, go on.
Sure. Okay, so what's the strategy from this? So these models, they can be studied. They're a bit idealized, but they can be studied. So we're going to do that a bit in the following. So I'll talk about how to make similar models that have interesting properties and then use them to explore the kind of behavior that we're interested in from active matter. So people in active matter, they're doing lots of simulations of lattice. Can we learn something about what they're doing by going back onto the lattice? Okay, so I'll talk a bit about a recipe for building these models, and then I'll do some examples. Okay. Right. So let's suppose we don't exactly like the model of Bourdieu, Tailleur, Erignou, and so on, for whatever reason. We don't like the swapping or whatever. What can we do? So how can we build a more generic active matter lattice model that has the properties that we want? So basically what we always have to do is if we want to have a proof of the hydro. So if we start with a nice equilibrium diffusive model where each orientation is a different species, so we had only 2 orientations, left and right, maybe we want to go to 2D and have a continuous set of orientations, so we need infinitely many species. So how do we do that? So we start with a nice model that we understand, where we can study multi-species physics, and then we get from MFT some sort of hydrodynamic equation, which looks like this. So we have the time derivative of the density of species alpha, is the divergence of a current, and the current is the mobility. Probably there should be a minus. No, there shouldn't. The current is a mobility, which will be a mobility matrix in general, times the gradient of a free energy. So this is going to be a function of the densities, and this F is going to be a functional of the densities. Okay. And in the case that we've just been discussing, this mobility matrix is not a simple thing. This mobility matrix has this slightly funny looking form, which is inherited from the ABC model, but the free energy is just the free energy of an ideal gas. But there are obviously other choices that we could make here, and the choices that we make are for the microscopic hopping rules, but then they give us different choices for the mobility matrix and the free energy. Yes. But this is the case that they study. But there's no reason in general to suppose that M is going to be anything simple. It's a bit simple, but it's not diagonal. So that's the first step, is you start with an equilibrium model that you understand. Then the step two is that you introduce the change in orientation process, so the process by which they change color. And you can do that often without breaking the equilibrium structure. So you can still have a model with detailed balance at microscopic level, and you can just introduce these reactions. And in the simplest case, you just have, simple flipping independent of everything. Then you have just this reaction rate is given by this thing, which I already showed you, just the difference of the rates, the difference of the densities times the constant. And alpha, remember, is the species which is either plus or minus in the simple. And then we have to introduce the self-repulsion, and this is where things become a bit more non-trivial, I would say. Well, it becomes more complicated. So there's going to be a new term in the equation of motion. So we do this again at the particle level. We know what we should do at the particle level in order to get the right kind of terms in our hydro equation. And the simplest thing that we can do in the example that I already showed you is that this JSP turns out to be, SP is for self-repulsion. It's in the same direction as the charge, has a parameter lambda in front. It's proportional to the density of the particles, as it kind of must be for advection. And then you get this 1 minus rho because, as I said to you, the self-repulsion only makes any difference when I hop into a vacant site. So that's why you get this 1 minus rho factor. Okay, so is this sort of clear? More or less? Maybe not. Okay. So M is the mobility. So M is the thing which converts forces into velocities, if you want. So this is the free energy gradient. So this is the thermodynamic force on species alpha. This is the thermodynamic force on species beta, but that can push around species alpha because of conservation laws and so on. So it's like a Onsager matrix, if you want, if you know that business. For SEP, it would be in one species SEP, it's rho brackets 1 minus rho. So it's the sigma of Kiran. You can get it from the, sorry, maybe I should have said that already. So it's going to be the noise correlation later. But the noise correlation and then. And if you want to have a thermodynamically consistent model, so if this self-propulsion wants to come from forces that act on individual particles, then the mobility should also appear in the self-propulsion. If you're applying a force E, then this would be the self-propulsive current that you get, and it would have a mobility in it. But in general, that's not true, and it's not true in this case either. So people put different things here in active matter, and there's, because it's not derived, because your model's not derived from forces acting on particles, you can put whatever you want. Or at least you can construct your lattice model or hopping rules however you want, and you can get whatever you get. M is the Onsager matrix. I'll say 2 words about it in a minute. Yeah.
Only the J breaks detailed balance.
Only the self-propulsion breaks detailed balance in the way that I've described it. Because if you think about the model that I said before with the 2 colors, it's an ideal gas with respect to the color and everything. I mean, you could do it different, but that's what it is.
Just to be sure, this is hydrodynamic limit, so no fluctuations at the moment.
Not yet.
So it's not MFT yet.
Not yet.
Although we don't agree what is MFT, nobody knows, but
this is just hydro. This is just hydro. Yeah. I think maybe it's the next slide or maybe next one. Yes.
In standard hydrodynamics, maybe I wouldn't put the R but I would put something like a J, that would be the Euler current, right? And the Euler current has can be any function of rho. It has certain constraints, like its derivative must has its Jacobian must be a certain formula that. So here is these constraints that you break to make the thing active.
This one you mean?
Yeah, J. Because I don't necessarily write it as M times. It's just I can write just an Euler current, right? Something that.
Yes. No, this constraint is really coming from the idea that. So okay, thermodynamic consistency. What does it mean? It means that your rates at the bottom level obey what's called local detail balance. And what does that mean? It means that the forward rate divided by the backward rate for any process, you can write as exponential of minus the energy difference plus the injected work.
And yeah.
And if you do that, then this E is something to do with the injected work. It's the injected work divided by the distance.
So my understanding is that you want to write a G which has a different form now like lambda rho alpha 1 minus rho, something like that. But I mean, in general, the J is not written as M times E is something more general than that's a function of rho, you know, like in generic hydrodynamics. Right?
So it is a principle of modeling in this business that you should be able to write it like this. Okay, it's a principle that some people like, okay? And they justify it based on the grounds of coupling to a heat bath and stochastic thermodynamics. Okay, so if you don't like it, I don't mind because I don't obey it.
Like, so I guess there are other principles which, I mean, like in GHD, for instance, we don't find J equals M times it's different.
No. But you have a different modeling starting point from what these guys are talking about when they talk about thermodynamic consistency.
But we do find currents have a very specific properties in general. One property is that the Jacobian of the current should be diagonalizable with real eigenvalues, and this corresponds to the sound velocities and all that stuff. So I wonder if this is what we break here.
I hadn't thought about it. I mean, I think because this diffusion is dominating everything, I'm not sure that sound is not making much sense here. I mean, yeah, it's a good thought. Okay, maybe I'm wrong. Okay.
It still makes sense.
Yeah, exactly. So can I move on and let's discuss it? Yeah. Good. Okay. So there's a lot of subtlety around this assumption, and if you read the MFT paper, they say it should be like this. They say this is what Kiran called sigma times nu. Okay, but in classical MFT, this would be sigma times nu. Yeah. Okay, and here it's not. That's all I'm saying. Okay, I'm gonna carry on. Okay, so now we're good. So the good news is that I'm writing this down as if I'm engineering PDEs, but I'm really not. I'm really engineering lattice models, and then I'm deriving PDEs, or I'm asking someone else to derive PDEs. But all this is coming from lattice model. And the way I've done it, I've introduced WASEP type scaling to get me this self-repulsion, and I've introduced very slow reactions. So that's not doing much to the local equilibrium states that are lying around in the system. And so what that means is that as soon as you write this down, you immediately know what to write for MFT, which is just that you take the diffusive part and you square it and you put the mobility matrix, and that gives you, so this is now the probability for a path. And a path is described by the history for the density, the history for the current, and then you also need the history for the reaction flux. So you need to know how many reactions you had taking you from blue to red and how many you had from red to blue. And then you can write explicit formula for the path probability, which is the probability that the empirical path looks like rho jk. So these hats mean empirical. So the probability that the empirical rho jk looks like some rho jk is given by the action, okay, and the action is the integral of the Lagrangian, and the Lagrangian is the current minus the current that you want to have, quadratic form of that with the inverse mobility matrix, plus something which comes from the reactions which I'm not writing down, but it's unpleasant. It involves Koch and arc-Schein and other things like this, but it's explicit. So if you do all the machinery, then as soon as you've got this, you've got this. It's just a bit more writing. So there's no freedom left in the fluctuations because everything is dominated by diffusion at the bottom. So Kiran, does that answer your question from before? Okay. So yes.
From what we were discussing yesterday, I guess it would correspond to adding a noise with a standard noise trend and then doing the path integral.
So you have to add the diffusive noise inside the square bracket, and then you have to add the reaction noise outside the square bracket. And the reaction noise is not Gaussian, by the way.
There was, sorry?
The reaction noise is not Gaussian. So it's like a sum of Poissons.
So you have two noise that you have.
Yes. So this K, this is coming from a noise on the reaction, so a noise on the color change.
Yeah.
And this is coming from a noise on the hopping. And both have to be present if you want to do it. And because the hopping is the reactions are very slow, so you don't lose it doesn't become Gaussian, you still have a Poissonian structure. I'm not sure if I would call it decoupling, but anyway, something anyway. Okay, fine. So this is the recipe, and it gets you all the way to MFT. So you have fluctuations at MFT order, you have WASEP, you have hydro, everything. And of course, it's still a lot of work because you have to engineer lattice models that give you the behavior that you want, but at least you can do something. Okay, so take a message, what should we remember? So we have equations of motion like this for the hydro, and then we have fluctuations. Each orientation is behaving like a separate species, so alpha is the orientation, and I want to have continuous orientation in a minute, because I want to put orientations on a circle, and then I'm gonna have an integral over species, so I'm gonna have an index theta. I'll have a variable theta instead of an index alpha, but okay, nothing will be done. We always have this weakly asymmetric hopping, which people don't like maybe, but that's what we have to have in order to be able to do the maths. And that means that the separate species survive as hydrodynamic fields. So if we didn't have, sorry, that's for the reactions. If we didn't have slow reactions, we would have just a one component, a one density with the orientations left out. But the orientation is a slow field for us because the reactions are very slow. Okay, and then we have the fluctuations from MFT, and the noise is just the equilibrium noise because it's the mobility. It's from the equilibrium model that we started from in the beginning. So just the diffusion. Everything else is just dressing the diffusion, this and this. Okay. So now I have a few examples. They become increasingly complex. Maybe some of them are more interesting, some of them less interesting. So I'll just get as far as I get. So the first thing that we thought about is from this paper with Clément and Maria and James Mason. And we came to this from a funny place. We were doing something different, but we arrived at this place. So what did we have? We had a 2D lattice model with on-site exclusion, no alignment. So the orientations just evolve independently of each other. But the orientations are continuous. So what you're seeing here is colored arrows, which indicate the orientations of particles which are sitting on lattice sites. And the colors, for some reason, indicate the orientation, who knows? But we wanted to get rid of this ability to swap places because we thought it was a bit nasty. And obviously, you can't do that in 1D anymore. You have to go to 2D, otherwise they can't pass each other and there's no mixing. And the color flipping is not efficient in mixing things, so you can't do it nicely.
How the translation happens is related to the orientation still?
Yeah, so they hop preferentially along the orientation, like some sort of cosine with the, take the cosine between the orientation and the...
You just take projection and then you...
Yeah, exactly.
Then which side would you jump to?
You can always jump in all directions, only to nearest neighbors, but you do it with rates that depend on the orientation. So think of the orientation as a force which acts in a particular direction, and then you just follow the force.
Thank you.
So if we come back to our recipe, the first stage is just to understand the equilibrium model. So turn off the self-propulsion, turn off the orientation change, and let's just try and understand the equilibrium model, because that's already something. And it turns out that the mobility in this case is a highly non-trivial thing. So this is where we really came to this from. So the mobility for, say, a few different species of set particles, which all have the same dynamics, but differ in their color. For this, you need to understand diffusion of color, and for this, you should read the book of Herbert Spohn, or you should read the papers of Kostel from the late 80s and early 90s, where they really thought carefully about this. And this stuff is all understood classically, but we didn't know it when we started. So what happens, so I'll tell you in case you guys don't know. So what is the mobility? What is the Onsager matrix or the noise matrix? It has a sort of diagonal piece and an off-diagonal piece, and it contains in it a function, which is the diffusion constant of a tagged particle in regular sec, density rho. So and what is that thing? What is that diffusion constant? There is no formula for it. There's no closed formula for ds. So there's no closed formula for the mobility in this system. But ds, it's just a function on 0, 1. It looks a bit like this. It's not very difficult to fit these red points with some sort of polynomial or ratio of polynomials or whatever you want. So in this paper, we actually tried to understand the behavior of this thing, and there's also quite a lot of classical papers about this. About its regularity and the variational formula for it, and lots of nice physics in here, which you could, if you're interested, you can find out about from Herbert's book, from Kiron's paper. But never mind. For our purposes, all that matters is that this matrix is quite complicated. There's no simple formula for it, but we have it under control. We can approximate it as much accurately as we want. Okay, and then this is the hydrodynamic equation now. So you're not expected to look at this in any detail because it does at least fit on a slide. Well, okay, maybe. So F now is the distribution function for the orientation and position of my particles. So instead of having rho alpha of x, I have f of x and theta. The discrete orientation alphas become a continuous orientation theta. And the angular dynamics is just pure rotational diffusion. So this term here is just the angular dynamics of the orientation. They're just doing pure diffusion. And then there are two terms here. This is the diffusive hopping term, and this is the advective term. And everything I've told you, so dE is the hopping rate, that's what I called D before. dO is the rotational diffusion constant. V0 is how much you like to travel in the direction of your orientation. So it's like a swim velocity. And then there are a few other things. So rho is just the density, the first marginal of F. P is the orientation, that's the kind of, and E is a unit vector along the orientation. So this is the polarization, the density. And then there's this curly D, which is 1 minus ds. Okay, is that everything? Okay, you don't need to worry about any of this. Just to say, the hydro, you can write it down. it's clear what's going on. And actually, we do know, we haven't written it, I don't think, but we do know what is the MFT associated with this, because it's just obtained by the computation that I showed you before. So you just have to write the formula. There's nothing to do. And the reason I'm showing you this picture with these particles organized now with a big void in the middle is that this system does motility-induced phase separation, and we were able to analyze it using this lattice model, and you can get kind of, I don't know. Certainly it's true that solving the hydro equations is a lot easier than simulating a very large number of on-lattice particles. So you have increased control over the large-scale behavior, which you can analyze using this model. But remember that the exponents are mean field-like. So in that sense, you don't learn much that you didn't already know. Okay. So what's the summary of this part? So we have motility-induced phase separation with continuous orientations in a lattice model. I don't think there's anything sick about this lattice model except for this WASAP scaling. The diffusion of color, so the fact that the intermixing of these differently oriented particles is non-trivial and has this self-diffusion affects the mobility in an interesting and, well, in a slightly complicated and potentially interesting way, which should not be forgotten about when trying to build this kind of model. So far, we didn't study fluctuations for this model at all, but we know what they are. So recently, we've been using this model to study wetting transitions in active matter. So if you put this material in a slit, you get wetting transitions between symmetric and non-symmetric wetting states that look like equilibrium wetting transitions, if anyone's interested. So there was actually, we actually posted a second installment of this morning, but whatever, never mind. There's a paper from June which probably has at least as much information. But that's the kind of thing that we're thinking about doing with this now, is we have a model where we can do controlled hydros, or we can do simulations, numerical calculations free of finite size effects, for example, which is a nice aspect. Okay, I've got 8 minutes, good. We sort of have 8 minutes. So I want to tell you something about fluctuations, because we're supposed to be doing fluctuations. And then I'll decide what else to say. So let's go back to the model with swapping, particle swapping places in 1D. But now we'll consider fluctuations for this. So I haven't really written everything down, but I did write down the mobility for this model, and everything else you can kind of guess what it is. And the fluctuations of this, so within MFT, one of the things that one can calculate are the fluctuations of time-integrated currents at very long times. So Kieran spoke about this on Monday. So you measure, for example, the total displacement of all the plus particles over some long time period, and this you would call the plus current. And this thing has fluctuations at large times, which are very small because the time is very large. And these you can analyze with macroscopic fluctuation theory. And actually, Tal Agranov came to Cambridge, and previously he'd been working with Sung-Hyun Rho and Yariv and Vivien, and he was already working on the fluctuations of the time-integrated current in this model, and they published one paper about the central limit theorem and one paper about the large deviations. And it's all nice. It's all nice. It looks a little bit like WASAP in a lot of ways. And then we wanted to talk about the fluctuations of the, yes?
We look at on the plus particles, there's a swap to minus particles, right?
Yes. So what did they do? Good question. So you take all the right hops by right moving particles for such time as they are right moving particles. So if I'm a right moving particle, if I'm a plus particle, my hops contribute to the plus current, J plus. And then if I change color and become a left moving particle, my hops contribute to the left moving current, J minus. So I contribute to whichever current is my species at the time that I'm hopping.
Okay.
Is that clear?
That seems to make sense, okay.
And remember, the hopping is very slow, so it doesn't, well, it does matter, but hopefully not too much. But yeah, that's what they did.
Right.
And I think that's the right thing to do.
Okay.
Okay.
Yeah. Thank you.
Yeah, good question. So in Cambridge, at that time, there was a lot of work going on about entropy production in active matter. And I'm not really going to talk about what the entropy production is, except to say maybe it's some sort of product of the currents and the forces. So you know from Onsager that force times current is sort of entropy production if you apply an external force to a system. So that's a quantity which is like a weighted sum of currents, if you want. And it was of interest to us because people were studying off lattice a lot and discovering lots of interesting things, and we wanted to see what we could learn from the lattice models. And in this business, and we did fluctuations in the sense of large deviations. And in this business, for the entropy production, we found something which had been anticipated before in MFT, but I don't think had been really demonstrated in real models, which is a tri-critical point in the dynamical phase random diagram associated with large deviations of the entropy production. And then we kind of later discovered that you can see these tri-critical points quite generically in these MFT type models under some conditions that we kind of worked out what they were. So this was an example where we were trying to understand active matter, but we ended up, I think, finding something new out about MFT. Well, not new about the structure of MFT, but a new result within MFT. And actually the KLS model, which was mentioned yesterday, actually has one of these tri-critical points in the large deviations of its current. And that's okay. So I don't really want to say anything more than this. I think for the experts, they've probably understood, and for everybody else, it's too much to try and explain in 2 minutes anything more about it. So let me just, in 2 minutes or 3 minutes, say something quick about a couple of other kinds of models that we've been studying, just in case it catches someone's attention and you can ask me about it in the next 2 days. So one example is a flocking model. So remember I talked about Vishek model, I talked about these birds that fly around. So in the flocking model, then we allow many particles per site. So it's like a zero range process now instead of an exclusion process. This was a model which Tal wrote down with Mike and Etienne. They are oriented, again, left and right with the same WASEP type. So if we turn off, so there is a model called active easing model, which is a bit like this, but we wanted something which is self-consistent, which is thermodynamically consistent. And what we mean by that is that if we turn off the self-propulsion, we get back an equilibrium model. And the equilibrium model that we chose is a model where we have a ferromagnetic interaction between red and blue particles of mesoscopic range, which means that particle interacts with neighbors over a distance L, which is very large compared to the lattice spacing, but very small compared to the system size. So that's like a mean field type ferromagnetic interaction among particles. And then what happens is, the red particles align with the red particles because of this equilibrium-like ferromagnetic interaction. So it's like an itinerant ferromagnet, if you want, because you have hopping. They have a density field and a magnetization. Okay, and then you turn on the self-propulsion to have the active matter behavior. So just to say, okay, what does this say? Never mind. That's the usual story. Okay, the hydrodynamic limit, you can derive it, and in this case, the dot is not too complicated. It's a model of gradient type in the jargon, which means that this hydra is not too difficult still. Okay, what do I want to say? So these are phase diagrams. So even at equilibrium, this model has quite an interesting phase diagram. Okay, so you can choose the density dependence of your alignment. So this alignment, this ferromagnetic alignment, is density dependent. You can choose that however you want. And so here's an interesting case where we choose the density dependence to be non-monotonic, which there's good reasons to suppose that might be generic. Then you get this quite interesting phase diagram with a homogeneous paramagnet up here, a homogeneous ferromagnet down here, and then two different phase-separated states between a magnetized and a demagnetized state. So this is like phase coexistence between magnetized, between a paramagnet and a ferromagnet at equilibrium. And then you turn on the activity, it becomes non-equilibrium. And you get new phases that turn up, including traveling phases, and this weird counter-propagating phase where you have, okay, just in 2 words, you have 2 different kinds of traveling waves that kind of pass through each other and travel continuously around the periodic boundary conditions. And there's a few examples of these weird counter-propagating states in these kind of models, but I really would like to understand better what is going on in these counter-propagating states. So this was an example, I think, of new physics coming from an MFT type lattice model. And then I don't have any time to talk about the last. Okay, so that's the flocking model. You get new and interesting phase diagrams, I think. Again, there's no fluctuations here, but we did analyze the entropy function, and we do have the MFT description again. And then the last thing, which I won't talk about, is we considered a mixture of active and passive particles And this has very rich and interesting physics that involves pattern formation over large scales. But you're all exhausted, so I'm not going to tell you about it. You can ask me anytime. That's the summary. I hope those of you who didn't know about active matter, maybe you've heard something about it now, and maybe there's some interesting things to discuss about MFT type models in the future. Thanks for listening.
Questions? There were many questions during the talk, but
So you had this relation between the mobility and the diffusivity of a tracer particle.
Yes.
Is this relation like something general that you derive? I mean, is something comes out from some bottom-up way where you generally relate this?
So for this situation of diffusion of color, so you have particles that are identical except for their color, then the interdiffusion of the different species, there are only two numbers which matter, which are the collective diffusion and the on hydroscales, the collective diffusion and the self-diffusion. So the self-diffusion is a tag particle, and the collective diffusion is like the one species mobility. Those are the only things that matter. And this is all classical, so this is in Herbert's book. I've lost the formula. Oh, it's here. So it's always like this, and what appears here, so this 1 minus rho is m of rho divided by rho, where m of rho is the collective mobility. So this structure is very, very general for this diffusion of color story, where all the species move the same but only differently. This story is completely general. And it's not difficult to work it out. I mean, you just think about green kubo for 5 minutes. So because this thing is obeying green kubo because it's the noise. So just think, yeah, maybe 10 minutes about green kubo and then you'll be done.
So in the case when you had the swapping, the original Julia-Taylor model, there, I guess you did have the DS term in the mobility.
So again, in the recipe, you start without any color change. And so no reactions and no self-propulsion. And you just have an equilibrium model. And the mobility is already fixed from there. So the color change doesn't touch the mobility because it's so slow. Right? So all the green kubo stuff is happening at the equilibrium level. That's the scalings are such that that's the case. So all the noise stuff is inherited from the diffusive physics without any self-propulsion, without any reactions. Is that your question?
It is. So I was trying to see that if I could take that model and go to the limit where. No, I think that is.
So there's the color change and there's the swap places. So the swap places affects the M a lot, but the color change doesn't on the scalings that we use.
Abhishek?
Of like scaling of parameters with system size that we discussed. And so instead of like thinking of L as the system size, is it, I mean, is it okay to just think of it as some coarse graining length scale, like some length scale over which the fields actually vary? I mean, because taking system size seems very unphysical, right? I mean, but if I just think of it as some, like, it's a coarse graining length scale, is that?
Yes, I know what you want to. Yes, I know what you want to say. So what you have to remember is that as soon as you do this, you end up with mean field critical exponents, pretty much whatever you do. So you can't sort of construct a way that this looks completely innocent, because it's not completely innocent, because it's killing for you all the critical fluctuations and everything. So there is some sort of mean fieldiness to this choice. And it doesn't really look like mean field, and you sort of think about it, and it's like, oh. But it's sort of mean fieldy. That's what it boils down to. So if you want it not to be mean fieldy, you have to go to something more like KPZ type scalings, right? You have to go to something else, like a real ASAP instead of a WASP. Does it make sense?
Size.
Yeah, so if you prefer, you can fix the system size and take the lattice spacing to 0, if you feel better about that. So that's another way to do it, is you take the lattice spacing to 0 at fixed system size. That's the proper maths way to do it anyway. And that somehow feels better, I think. But then you've got a very large number of particles in a very small space, which is kind of how you get the mean field. I mean, we could discuss maybe. What was the one from Jorge?
So if I put sources, I consider an open system, and I put sources with suitable chemical potentials, equal chemical potentials, so that we are not driving the system externally. We are not in equilibrium, but we're not doing anything. And then I do a phase diagram of chemical potential versus mobility or the relevant parameter. Would that be, because the phase separation one sees here is a bit, one doesn't usually study ice or water by considering a multi-phase system. You use a chemical potential and then it's easier, no?
It's a very good question. I mean, I guess there is no guaranteed equivalence of ensembles here with this kind of business, because so it's not innocent what you're describing. So we did something a bit crazy. We actually did diffusive hard rods with constant pressure, and then we did some large deviation type things. And so I guess it's not quite the same, but I'm not sure about equivalence of ensembles. That's what I'm trying to say.
So if it's not sure, wouldn't it be a nice exercise to try to
Yes.
see if there is or not?
Yes.
Or you're sure there isn't?
No, I'm not sure of anything. I feel I should know. I feel like I should know. But off the top of my head, I don't know. It would be great to look at it. I do agree completely.
Thanks.
Maybe I want to still understand your message. So at some point, I think you said that maybe you're trying to use MFT to create nice model, right? So, no? So as a kind of conclusion, what is the recipe to create a new nice model? So where's the starting point?
Yeah. So, I mean, I like a lot, which I didn't talk about. I like a lot this model, where you have a mixture of active and passive particles.
But this is a microscopic model, right?
This is a microscopic lattice model.
Okay.
But lots of people are studying off-lattice models like this, and they do computer simulations, and they have conclusions, and they have horrible finite size effects, and it's difficult to understand. And now we say, well, we have this model, we have exact hydro, we can do for free simulations that they could only do with infinitely many particles. We can do easily hydrodynamic simulations of models like this that are accurate representations of an underlying particle model, and we know what is the particle model. And this model has super interesting behavior, and well, has interesting behavior.
So to find this model, did you use kind of MFT?
For this model, so we derived the hydro for this model using MFT type hydro arguments, and we know the MFT for this. We haven't done anything with the fluctuations for this, but we know what are the fluctuations. So I'm mixing up lattice hydro with MFT a bit, because for me they are kind of.
This point was not so clear.
Yeah, for me they're kind of two sides of the same coin, I think, because we have the MFT for this model, even though we've never used it.
MFT means what?
Means the action principle for path, for large deviations of paths.
With the noise?
With the noise, yeah. Yeah, because
it's beyond hydrodynamic limits.
Yeah, because it follows from the argument that I gave. Yeah.
You start from some hydrodynamics from continuous model, then create MFT and try to find some nice lattice model, something like this?
Well, I think we started from the lattice model because we started from this lattice model because we knew we could derive hydro for it. And we thought something interesting would pop out from the hydro. We thought it would have interesting behavior, and it did, and we thought it would be tractable, and it is a bit.
So you did not really use MFT to create this model, right? No.
We used. Okay,
maybe
it's a bit semantic to me. I mean,
maybe we can discuss.
We were studying these kinds of models, and this is really a dressed up WASEP. So if you think WASEP is an MFT model, for me it kind of is.
Okay, you call it WASEP was an MFT model.
Don't you think, or you don't?
Okay, maybe it's just a question of well,
yeah.
okay, so maybe we can discuss later. Thank you.
maybe we can, because I had a little question, dependence on dimensions, something more interesting happens in 3D or it's the same kind of, phase separation?
I don't know of any big changes between 2D and 3D. Nobody likes doing orientations in 3D because no one likes unit vectors. I guess you could do a variable length.
I mean, birds are in 3D.
Yes, yes, yes. But if we have mean field, then, I mean, all of the Andrea Cavagna business, of course, one could try, but that's one level more complicated then.